Today will be our last lecture about the physical optics. So you can see here, I say it is chapter 28. It is correct, but I am only going to focus on these three subsections of that. And there are two reasons for doing that. First, you can see that actually they are just the continuation of the discussion of the chapter 26. And also, these three subsections will play a very crucial roles when we try to study the quantum physics. And also, today will be the first lecture. I will leave one or two conceptual quiz unanswered. And after you watch the video lectures, please email me your answers and with the explanations, such that you can earn the bonus point. Also, if you have any questions about the homework, please try to contact me. We can try to meet through the Microsoft Team and any approach. So today we are going to study the thing we have actually studied before, but we try to make the discussion more general. So you definitely have heard about what is superposition and interference. But today we are going to study is that when you have two different sources produce the wave, and what kind of interference and the superposition will happen. Then we are going to study, based on that, what is the so-called Young's two-slit experiment. And finally, we are going to study how does the interference happen when there is a reflective waves. Now let's try to first refresh our memory. So in the previous chapters, when we study about the interference and superposition, what we mean is we have two different kinds of interference, constructive and the destructive. So for the constructive interference, I say that it happens only when the two waves are in phase. And what do I mean in phase? Is that when the two waves combine together, you can simply add the amplitude directly. This is a concept of the constructive interference. And all other kind of interference are considered of the destructive interference. And here, the example for the destructive interference is for out of phase, which means that the position of the crest of the first wave will be overlap with the flow of the second wave. So when they overlap, actually the amplitude is a subtractions. But you will find out that after the interactions, the waves still will propagate in their original amplitude. Okay, so they will stay the same. And the wavelengths and all the properties stay the same. So why we are interested about studying the interference, especially again in these chapters? Because you will find out if you have more one sources can produce the wave, actually you can observe many interesting phenomena. So today, let me try to define two words we are going to use frequently in the following lectures. So the interference is only noticeable if the light source, for example, now we have two. These two light sources are monochromatic. So what do we mean by the monochromatic? It means that the two light sources have the same wavelengths. They all produce the same wavelengths. So here, they are very good examples. So this is a wave produced by the first source. This is by the second one. And you can see, based on the definition of the wavelengths, they have the same wavelengths. Then we say that is the monochromatic. So this is the only scenario we are going to focus in these lectures. And the second word is the coherent. So in physics, when we say the coherent, it means that these two waves maintain the same phase relationship over the space and time. So you can see that these two actually are in phase. And when they happen in phase, the position of the crest is the same for the first and the second one. So now we are going to focus is that now you have the two sources produce the wave, and when they overlap, what will happen? So here is the case. So we definitely still have the constructive and the destructive interference as we studied before. So this one, if it is a constructive interference, which means it is in phase as we just mentioned, so you simply just add the amplitude. And for the destructive, we say they are out of phase, and this is the perfect out of phase one. So you will see after you add them together, the amplitude just becomes 0. But in fact, what we mention here has a very intrinsic meaning, is that different sources maintain the same phase relationship, is that this is the constructive interference, but this is also the constructive interference. You will argue that there is no difference between these two. The answer is yes and no. You can also understand the difference between this one is their phase difference is 1 full wavelength. So it is not in phase, but they are out of phase for 1 wavelength, so eventually they become in phase again. So this is the reason that now the difference of the phase is related to the difference of the wavelengths. So you will see that this point with a more clear pictures in the following discussions. So now you are provided 2 antennas. They produce the monochromatic wave. So they have the same wavelengths, but they are not necessarily in phase, okay? So when the wave propagates out from the first source, it is as a waveform, and there's a second waveform. Apparently, these 2 wavefronts will interact with each other. So here, there are several positions. So the best way to understand the P0, Q1, P1, Q2 is that they are just the position of the observer. So depending on where you stand, you will find out. When you try to observe the wave propagate from the 2 different sources, the wave pattern you observe is different depending on the position. So here, the constructive happens at P0 and P1, and the P2, and vice versa continue, and also in these directions. And the destructive interference happens at the position of Q1, Q2, Q3, vice versa, continues upward and downward. So when we say it happens, there's a constructive interference happen as a P0, which means that the path lengths from the 2 different wave sources differ by an integer number of the wavelengths. That is what we just say here. As long as they are differed by an integer number of the wavelengths, here it is 1 full wavelength, then we will say that these 2 are in the so-called constructive interference. And for the position P0, you will find out the difference of the path length is 0 integers of the wavelengths, so which means they are perfect in phase. But P1, the difference of the path length is 1 wavelength, which is the case we just mentioned here. So you can consider that this is the P0 for the first diagram, and this is P1 for the third diagram in the previous lectures. And this is the constructive one. And how about the destructive interference? So that happens when the difference of the path length is half odd number of the wavelengths. So for example, 1/2, 2 divided by 2, and 5 divided by 2, this kind of number. So this one happens for this one. So you can consider the difference of the 2 phases is half of the wavelengths. So this is actually what happens for the Q1. And for the Q2 will be 2/2 wavelengths. So now you can see this is how we define the constructive and the destructive interference by simply consider the concept of path length. And you'll find out this is a very crucial concept. So now let's summarize what we have to study. So if you have 2 path lengths, so no matter which observer you are talking about, for example, if you are standing at Q1, you can always define the so-called path length from the first source, which is L1, and the L2 from the second source. Yeah? So this L1 and L2 is different for different observers. So depending on where you stand, then they will interfere constructively or destructively. So to write the result based on the formula, this is the case. If the difference of the path length is an integer number of the wavelengths, then that is the constructive interference. If the difference of the path length is the half wavelength multiplied by integers, then this is the so-called destructive interference. Okay, so this is basically two formulas summarize what we just said. So how to use this formula? So for the P0, it is at position m equal to 0, and P1 is at position m equal to 1. They are the constructive one. And how about this Q1? Q1 is the first destructive interference, so it happens at m equal to 1. So 1 minus 1/2, it is 1/2. So the difference of the path length is 1/2 of the wavelength. And for the Q2, it is 2 minus 1/2, it is 3 divided by 2. So this is basically repeat what I just said. Now you can find out how to define the interference using the concept of the path difference. Now let me give you examples. So if you have if there are two persons, and one standing at the P0 and the other one is standing at Q1. So even those based on this notation, you can probably give a guess. But sometimes they will not even give you this kind of hint. So the difference, the position between these two length between these two positions is y. So what kind of information is given? First, it is the same frequency, so it is a monochromatic source. Now, the friend who is equal distance from the antenna at position P0 receive a very strong signal, but the friend at position Q1 they receive a very weak signal. So not a surprise to you, this is a constructive and this is this constructive interference. So they want you to find out the wavelengths for the radio because they all have the same wavelengths. Yeah? If you are given the distance d, which is the separations between the two lights, the wave source, and the L is the distance, vertical distance from the source to the observers, and the Y is the separation between the two observers. And now they also want you to assume that Q1 is the first point of the minima signals. So which means that you can basically assume it is not Q2 or Q3, it is the first destructive interference. So this is all the information given here. So how do we find out the wavelengths? So we have to refresh our memory. This is the definition for the constructive and destructive one. So therefore, we know that now for the destructive interference, that the path length difference is the half of the integers. So this is a destructive one. So we want to calculate the wavelength, so which means we have to calculate the path length L2 and L1 to the position Q1. Agree? So we have to find out L1 and L2. So what is L1? So you can use the trigonometry relation I show here. So the L1 is this one. So if you look at this triangle here, so for this triangle, the length of this end is capital L, and the length for this side is 2d minus y, because the distance from the source to the center is 2d, yeah? But the Q1 is y above the dashed line. So therefore, the distance from the source to this triangle here, this is 2d minus y. So from this triangle, you can calculate L1. And how about L2? L2, you should use this triangle here. This triangle. So apparently the length of this side is capital L, but now the length for this side is 2d plus y. So now use the trigonometry relationship, you can calculate L2. So now L1 is 14.1 and L2 is 15.1. So the difference will be the 1 kilometers. And the wavelength is actually 2 times 1, so it is 2 kilometers. So that is how you use that. So remember that this is only true for the constructive interference.